Greetings, it's a great honor to receive this prestigious award. I express my heartfelt thanks to all the researchers involved in our project. My humble gratitude to the committee members who selected us for qualifying for this award, and this will certainly motivate us for our future research works. To begin with, here is our research project entitled Electrochemical Characterization and Joule Heating Performance of Polyaniline-Incorporated Fabrics. This project is led by Dr. Mustafizur Rahman, Professor, Faculty of Mechanical and Automotive Engineering Technology, University Malaysia, Pahang, and will be presented by me, Muhammad Shohan Parvez, Assistant Professor, Department of Textile Engineering, Pune University of Engineering and Technology, and a Postgraduate Fellow at University Malaysia, Pahang. To begin with, here is our outline of this project. And it will start with the problem statement and some introductory backgrounds and objectives. And we will find some research methodology technique involved in this project and subsequent characterization test to validate the results. So as we can find here from the introduction part that with the potential range of the wearable electronics is now becoming the key attraction with the latest technological advantage, and the wearable electronics is not only confined to only the clothing or the electronics. It has some far more larger perspectives right now. So it actually it's what are wearable electronics? It's actually gonna reduce the human and electrical interaction, and it will make the interaction much more easier. This is the primary objective of wearable technologies. However, there are some additional importance and advantage of this wearable electronics, including they have some superior mechanical flexibility, some electrical and electrochemical performance, and of course, the clothing will induce comfort and some other functional attributes at the same time. But however, there are some problems. So as we are talking about clothing and electronics, but electronics come out from a bulky structure, and the bulky nature, they are from the rigid nature. But so seemingly, it was difficult to convert to reuse these electronics into clothing. So here is the key pathway, so we can make the fabric into a flexible electronics, and that is as the textile surface is usually completely inert form. So in order to make it perform in an wearable electronics, we need to make it a conductive surface, and that's the first step of making the electronic textile. And how we can make this conductive fabrics? Well, previously the ways usually involved with metallic components interaction, but with time we are the researchers have found a lot of intrinsic conductive material that can be induced with the clothing surface. There are many ways we can make the clothing surface, and there are many materials right now, and among them, conductive polymers are one of a kind of these intrinsic conductive material, and conductive polymers are really fascinating as they inherently harness conductivity within their structure, and these are the main reason that we are focusing on conductive polymer, and the abundance, the synthesis process are also easier. Most importantly, the processability with textile surface and conductive polymer is much more feasible than any other forms of conductive materials. Later, we have found a bunch of conductive materials, conductive polymers especially, and that are actually currently used by the researchers. However, every conductive polymers have some specific advantages and as well as some challenges. So we are focusing on a brief summary. Sorry, here we actually found that there are aids with synthesis. There are advantages with the conductivity but there are problem with some toxicity, the cost, the processability, and the end use. So, among the conductive polymers, there is all polymer, and that is called polyaniline, also known as spinning. Actually, this polyaniline has been used for hundreds of years, and from our literature review, that this is one of the most abundant and one of the most explored conductive polymer in our arena. But this polyaniline is still been fascinating. It's still been of use, fascinating uses. But why? Because the synthesis process is much easier, and the processability with textile is much easier than other materials. And however, the conductivity is not as desired as from other materials. So in order to make the conductivity higher, there needs to be some improvement with the conductivity, and so that we can make the best use out of polyaniline. So our basic understanding from this research is to understanding the correlation between the synthesis polyaniline, the morphological and electrochemical analysis of polyaniline-induced fabrics, and eventually to use the fabric as a heating object for future uses. And here is the research methodology, how we are gonna make the conductive polyaniline and the conductive polyaniline fabric. However, we have used P.PSS as well to check the conductivity to make a comparative study with P.PSS. But how we are going to make polyaniline? Well, we have used a pretreated cotton fabric, which is pretreated with sodium hydroxide, which is found to be an effective measure. And also we actually use aniline and some ammonium persulfate as oxidant and aniline as monomer. And there is some specific amount that we are going to mix. We have mixed, and thereafter we actually formed polyaniline using a continuous stirring and the dropless addition of ammonium persulfate into monomer solution. But however, there should be this as this is exothermic reaction, the temperature should be in between 0 to 4 degrees Celsius, so that the oligomers formation is less than and the reaction can be formed successfully. So upon the addition, and we actually waited for 30 minutes for the perfect formation of polyaniline, and thereafter we can found the in situ polymerized cotton fabric as our final product. And here is the actual process that we are actually discussing previously. And we at the final process we found the polyaniline induced cotton fabric. And here actually we have performed some morphological analysis, and we from the FTIR analysis we have found that the polyaniline has successfully incorporated with the cotton surface. This can be at first this can be visibly confirmed from the color of the fabric. Previously it was like a white fabric, or we can say light white fabrics, but with the successful impregmentation of the polyaniline, it's become a darker green, bottle green colored fabrics. And that actually visually signifies that polyaniline is formed successfully. And also from the FTR analysis, we have found some distinctive peaks that actually justified our theory. And that is, we found the quinone and benzoline. This is actually the base form of the polyaniline, as we have found earlier. And it actually confirmed the protanoid emeroid salt in the fabrics. And also, as we, for comparative purpose, we have used P.PSS. This is also confirmed from the FTR analysis, as we can find that the distinctive peaks that is more flattened with the impregmentation of P.PSS. And as we are saying that it can be visually distinguished. And here we have the optic digital microscopic image, and there is some untreated cotton at the left, and the polyaniline deposited cotton at the right. And we have found that it's much of a darker green surface after polyaniline deposition. And here is the same micrograph, and if we can look closely, that we can find that before the polyaniline treatment, the surface is much flat, cylindrical, and flat. However, with successful impregnation of the polyaniline, it's become a grain-like material on the treated fiber strand, and it's almost everywhere and deposited evenly through the fabric. And this is a closer view of the polyaniline surface. Here you can find the polyaniline is formed as a granular form on the fiber strand, and we can find it from the magnified images, much magnified images, that polyaniline is successfully impregnated on the surface. And later, from the elemental mapping, we have actually found that how much the amount are actually properly distributed over the cotton fabric. And we have found that the green one, the nitrogen one, and the oxygen one, this actually signifies the formation of quinine and benzoate. And before that, there is from the EDX mapping, we have found that it was not earlier like the chlorine and the chlorine and the nitrogen one. However, with successful implementation of protanoid amaranth salt, this actually found that these are successfully formed in over the yarn. And here is the result of our resistance, and we can find that we actually follow for treated pieces for 10D, and we have confirmed from different dopant materials while synthesize the polyaniline, and we found that the higher the dopant level, the higher the conductivity, I mean the lesser the resistivity. And in respect with the resistivity, we have found with that the 3 molar hydrochloric acid will be are showing the best result for the reduced responsibility. And there is significant improvement from the non-treated fabrics and the treated one. There is a significant difference, and this actually signifies that the pre-treatment process with the sodium hydroxide is actually doing some serious improvement with the conductivity. And we also we're focusing on electrochemical attributes. We are focusing on the cyclic voltammetry test, and we have found that this fabric is showing distinctive redox peak that actually signifies the successful redox reaction is formed within the fabric fabric itself, if we can use this fabric for electrode material. And here we can find the energy energy dispersive X-ray spectroscopy. And here we can find that previously with the untreated cotton, there is only oxygen and carbon. And after the successful impregmentation of polyaniline, there is some nitrogen and oxygen, which actually due to the benzoate and quinoid structure, and the chlorine is due to the acid, the protanoid acid solution. From the TGA, thermography-metric analysis, we have found what about the thermal stability of this fabric? So here you can find that all the fabrics, the untreated one at the left and the treated one at right, that there is an initial weight loss, which is 3 to 7%, and a prominent endothermic peaks indicating a breakage of cellulose at this point, at this temperature, and which is 324 degrees Celsius for the treated one. It is actually kind of less than the untreated one, but with the higher residual highest residue is found for polyaniline itself. But if we can compare with the other acidic solution, we can find that the higher dopant concentration is much stable than the rest. And finally, we have used for Joule heating performance for polyaniline treated fabrics. And this is found that within, we actually use a temperature, a volt, a source of 15 volt driving voltage is applied. And within 15 to 25 seconds, the temperature actually drove to 37 degree, over 37 degree. And it's going to be stable for a while as well. Around 1 hour, it can be stable. And this temperature can be raised to 38 degrees Celsius within 25 seconds of time. So this signifies that the fabric can heat up with given voltage if we are intended to do. So our proposition is these fabrics can be used for many purposes, for many heat generation purposes. But among them, we actually focused on heated pad that can be used for a seat, so that where it's necessary, this fabric can be heated. Usually, these are making from metallic metallic yarn and metallic surface. This is bulky, this is rigid, and sometimes it actually heat up the whole thermoplastic material and it melt out and it cause hazard. But if we can change this to the fabric based electrical pad, this can be uh, the heat generation can be within it, so that our skin can tolerate, and it's not gonna be over with changes of volt. So we can achieve an optimum level if we can use this conductive fabric as a heating generation pad upon providing with a certain amount of voltage. So in conclusion, we have found that yes, the pre-treatment process is significant for the conductivity enhancement, and it can actually reduce the resistivity to 1.3 kilo per centimeter. And this is one of the reasons we can use, well, we should perform the pre-treatment process and the latter process. And this is also checked with P.PSS, and it's actually the resistivity is even lower if we are using P.PSS and fabric with 10 deep, and this one single in situ polymerization can overthrow the P.PSS material. So this is our findings, and thank you everyone for your kind presence. And we again render our gratitude for the committee for selecting us for this prestigious awards. And thanks everyone. Thanks a lot.